Okay, let's talk about exponents. You definitely remember these from school, right? But what you might not know is that there's kind of this secret language hidden inside them. So today, we're going to crack those codes and see how these little numbers can make really complex problems surprisingly simple. All right, first things first, a quick pop quiz. In this expression, 2 to the 5th, what did your teacher tell you to call that little 5 floating up there? Come on, I bet you have an answer on the tip of your tongue.
And boom, right out of the gate, we are busting our first math myth. You were probably taught to call the 5 a power, right? Well, here's the real story. In precise math terms, the 5 is the exponent. The entire thing, 2 to the 5th, that's the power. I know, it seems like a small detail, but trust me, getting this right is the key that unlocks everything else.
So let's dive into that. Let's officially clear up this common math lie. Because understanding the real difference between an exponent and a power, well, that's the first step to actually getting these concepts, not just, memorizing them for a test.
Okay, let's look at an example. 7 cubed. That little 3, that's the exponent. It's basically the instruction manual. It tells us, hey, multiply the base, 7, by itself 3 times. Now, the whole shebang, 7 cubed, which, by the way, equals 343, that is the power. So think of it like this. The exponent is the command, the power is the entire operation and its final result.
But why even bother with this stuff? Did some mathematician just decide to make our lives harder? Nope, not at all. It's actually the exact opposite. Exponents were invented because someone desperately needed a shortcut.
I mean, the reason is just super simple. Think about it. Writing out 2 times 2 times 2 times 2 times 2 is a total pain. It's slow, but writing 2 to the 5th, that's fast, it's clean, it's efficient. And that's it. That's the whole origin story. Exponents are nothing more than a brilliant piece of mathematical shorthand. Okay, so now that we've established they're just shortcuts, let's learn the rules of the road for how to actually use them. We're going to start with the 2 most fundamental rules, the ones you'll use when the base number is the same. All right, first up, we've got the product rule, and it's simple. When you're multiplying 2 powers that have the exact same base, all you do is keep the base and just add the exponents. It's literally a shortcut for our shortcut. But hey, don't just take my word for it. Let's prove it. Let's see why this works. On the left, you see the long way, right? 2 cubed is just 3 2s. 2 squared is 2 2s. You put them all together, what do you get? 5 2s, which is 2 to the 5th. Now look at the right. Using our new shortcut, we just do 3 plus 2 and we get 5. Same answer, way less work. See? It just makes sense. And next up, we have the quotient rule. And, just like you'd expect, it's the logical opposite of the last one. If you're dividing powers with the same base, you just keep that base and, you guessed it, you subtract the exponents. And yeah, we're going to prove this one too. Look at the long way on the left. We've got 5 2s on the top of the fraction and 3 2s on the bottom. We can just cancel out 3 pairs of 2s, right? And what's left? 2 2s on top, or 2 squared. Now, the shortcut on the right gets us there in one move. 5 minus 3 is 2. The logic is flawless. Okay, so we've got multiplying and dividing down. But what happens when you start, stacking these things? When you put an exponent on top of another exponent, what do you do then? Well, that brings us to 3 more really elegant rules. First is the power of a power rule. When you raise a power to another power, you just multiply the exponents. Easy. Next, the power of a product. Got a couple of things being multiplied inside parentheses with an exponent on the outside? Just distribute that exponent to each little piece inside. And you know what? The exact same logic works for the power of a quotient, or a fraction. All right, now it's time to tackle the ones that usually trip people up. The ones that feel kind of weird, maybe even a little arbitrary when you first learn them. I'm talking about the 0 and negative exponents. But as you're about to see, they're not weird exceptions at all. They're actually totally necessary results that make the whole system perfectly logical and consistent. Okay, let's get right to it. The big one. Why in the world is any number raised to the power of 0 equal to 1? It just feels wrong, doesn't it? Like, shouldn't it be 0? Well, nope. And it's not some weird mathematical magic trick either. There's a perfect explanation. So let's just walk through the proof, step by step. Step 1, start with something we absolutely know is true. Any number divided by itself is 1. So 3 to the 4th divided by 3 to the 4th has to be 1. We're all good there. Step 2, now let's take that exact same problem and apply the quotient rule we just learned. We subtract the exponents, right?
4 minus 4 gives us 0. So we get 3 to the power of 0. And here it is, step 3, the big aha moment. If that same expression equals both 1 and 3 to the 0, then 1 and 3 to the 0 must be the same thing. It has to equal 1. It's the only way for the rules of math to stay consistent. It's pretty cool, right?
So what about those pesky negative exponents? Honestly, this one sounds way scarier than it is. A negative exponent is not about making a number negative. It's just an instruction. It's telling you to flip it. Or, the fancy term is take the reciprocal. All you do is move the power to the other side of the fraction line, and poof, the exponent turns positive.
Okay, we've defined our terms, we've learned all the secret codes, we've cracked the system. Now it's time for the best part, the payoff. Let's see how all these little shortcuts team up to help us just tear through problems that look impossibly hard at first. All right, get a load of this thing. I mean, wow. Fractional exponents, nested parentheses. This looks like something straight out of a math nightmare, designed to make your head spin. But I promise you, it's not as bad as it looks.
Yeah, I know, it looks tough, but we're about to use all those shortcuts we just learned to completely unlock it, one step at a time. And the best part is, you already know everything you need to solve this. So let's do it.
All right, let's break this beast down. Step 1, we're going to tackle what's inside the parentheses first. A fractional exponent, like 1/3, that's just a fancy way of saying take the cube root. So the cube root of 8 is 2, and the cube root of 27 is 3. See? Simple. Okay, step 2. Our expression just got way friendlier. Inside the parentheses, we now have 2 plus 3, which is 5. So the whole thing becomes 5 times 5 cubed. Moving on to step 3, we can use our product rule here. Remember, 5 is the same as 5 to the power of 1. So 5 to the first times 5 cubed, we add the exponents. That gives us 5 to the fourth. So clean. And for the final blow, step 4, we use the power of a power rule. We've got 5 to the fourth, all raised to the 1/4 power. So we multiply the exponents, and 4 times 1/4 is just 1.
And there it is, just like that. That massive, ugly, intimidating expression, it all boils down to one simple, clean number, 5. That is the power of knowing these shortcuts. So here's the main takeaway, the thing I really want you to remember. The laws of exponents, they aren't just some random list of rules that you have to memorize. They're a really elegant, totally logical system of shortcuts, where every single rule connects to and proves the others. So from now on, whenever you see some rule, I want you to challenge it. Don't just memorize it. Ask yourself, okay, what's the shortcut here? What's the clever code that's just waiting for me to crack? Now go find out. Thanks for watching.